The next topic is chapter 13, and it's about electric circuits. So what are electric circuits? What is the simplest kind of an electric circuit that you may encounter? Those things will be pretty much covered in this part of the course. So first of all, what is an electric circuit, and then then how do you connect circuits? Like there are variety ways like to connect circuits. Maybe there is a series connection, there is a parallel connection. Then how do you differentiate one from another? Then this is where we will be learning about that. Okay. So in general, like if you consider the very simplest kind of circuit, you can imagine, like, for instance, take a cell, like a battery or something like that, and let's say the battery is like this, okay, and then you take a small bulb, and let's say this is the small bulb, right? Then let's say you're going to connect this with a wire, okay, and then someone will give you like a wire, and then you will wrap the wire around here, and then you're going to bring the battery in contact with the bulb right here, like that. Okay, so when you do that, what's going to happen is like the bulb will light up. Okay, this is like the simplest circuit you can come across, right? This is the very simplest electric circuit you can come across. But like right now you're connected with a computer or like a home, and then your computer is directly connected with the power outlet. Then that is a circuit. That's part of a circuit. Of course, it's part of a complicated kind of circuit, but this is the very simple kind of circuit that you are going to come across. So if you look at here, what are the items that got involved in this overall stuff? So you had the bulb, right? So the bulb was there, and then there was a wire, and of course there was battery. Okay, so each one of those things, they have their own functions, right? So the bulb, the wire, the battery. But how do they get involved in a circuit? And then, like, the battery is pretty much the source of your energy, right? The battery, you can consider it like as your source of energy. All right. So what's happening is like there is a chemical reaction happening inside the battery, and then it keeps the positive charge up here, and then it keeps like the negative charge around here. So like there is like a negative terminal of the battery down here, and then there's a positive terminal of the battery. So the purpose of the battery is just like to keep those two charges away from each other. And then literally, like, what you try to do is like you try to have a flow of electricity. So what's going to happen is like when you create a connection between here and the bulb, what would happen is like electrons will start to flow through the wire. Okay, so not the positive charge, the negative charge are the one that flow through the wire. Then, because you remember when we defined conductors, like a conductor means a material that has a property of like letting its electrons to roam around, right? So as a result, like because of this potential difference, we usually call it potential difference between the two terminals, then there will be a flow of electricity. Okay, then there will be a flow of electricity. Then that flow of electricity is the one that is responsible for having like this overall setup to work. Okay, so there will be a flow of electricity. I mean, flow of, call it charge. Okay, we're going to define it in a moment. Then, if you consider that flow of charge per unit time, right? So that's what is called current. So by definition, current is the amount of, so current in the battery is the flow of charge per unit time. Okay, so how much current is flowing, like how much charge is flowing through the wire per unit time. That's what we call it. Like, so so we come across like with a new definition of like something that flows. So something that flows in the wire, those charges, we define them like as current. Current means like the flow of charge per unit of time, and it's symbolized as uppercase letter I. And we say that like it's Q over time, right? Q is charge and T is time, right? So Q is charge and T is time. And of course, I is our current. So something that you need to keep in mind here is like, we already defined like what Ohm's law is in the lab, but we didn't have the time to cover the theoretical background. So this flow of current is what is resulting in the lighting up of the the bulb. Okay, so then this is what we define as current. Okay, and there are other things that are associated with it, like that will just, so what is driving the flow or this flow to happen is something we call it like voltage. Okay, so the voltage is like the potential difference between the two terminals. Okay, because there is a positive charge on one side and there's a negative charge in one side. And then what's going to happen is like there is a potential difference. It means like there's a lot of extra negatives on one side and then there's a extra positives on the other side of the battery, right? So as a result, like if you connect those two terminals, then what you get is like the flow of charge. Automatically charge starts to flow because like the negatives will be running away from their negative peers and then they want to go and then join the positives, right? So the potential difference is voltage. Okay, so between the terminals, the potential difference between the terminals. Okay, so you need to keep that in mind, like terminals. So as an example, let me put it this way, like, so let's have the battery by itself. So let's have the battery by itself like this, and then take the wire and then connect it with the battery without having the bulb. What do you think is going to happen? All those negative charges and the positive charges up here, what was going to happen is like all the charges will be exhausted in a very short period of time. Literally, you will kill the battery in a short period of time because there is a significant potential difference between the two terminals. We usually get a cell of like 1.5 volt. If you have a triple A batteries, those small batteries that we commonly use for your computer mouse, keyboards and things like that. They are commonly 1.5 volt, right? That's the potential difference between the two terminals. You let those two things connect by just a random wire, then the potential difference is going to get exhausted. That means like there will be a balance. If there is a balance, then there is no any kind of electric field between the two that will drive the electrons from one terminal to another terminal. Okay, So then what is the purpose of having the bulb? So the bulb is made of some kind of material, right? Then it has like those little filaments, right? And those little filaments are like, they're made of, if you look at it, like very, very tiny kind of metal. And of course the material is different that can resist a high temperature. If you look at like the filaments are like very, how do I put it? Like the radius of those filaments are very, very tiny. So since it's very tiny, what would happen is like when you connect the terminal, what's going to happen is like when the electrons try to pass through the filaments, right? Then since the filaments are very, very small in diameter, what will happen is like they will try to restrict the flow of the current, right? That means when the electrons are trying to pass through this, or the charged particles try to pass through the filament, they are going to create a lot of heat eventually because they are very crowded in a very small area. Then eventually this thing starts to get heated up, and then this thing starts to glow, literally, right? That's how bulbs normally work. But the main purpose here, what we need to pay attention is the filaments restrict the flow of charge. Okay? So now the bulb is resisting the flow. Then we call the bulb our resistance. So the bulb is your resistance. So the resistance is part of the circuit. Rather, resistor, let me put it as a resistor. Resistance is the physical quantity. It's part of the circuit. That controls, you can call it controls or resists flow of current. Okay. So, sometimes like, which one is easier to let water to pass through? When the pipe is bigger or when the pipe is smaller? If the pipe is bigger, you just let the water flow freely. But in a very constricted area, right, the water fights to pass through it, right? So the same is true like in the bulb case, like, that filament has very tiny kind of radius, and then the electrons try to pass through it. They get restricted, and then like there will be a heat up, like because they are trying to squeeze themselves through in a very small area. Then eventually, like, then that thing starts to heat up, and then it starts to glow eventually, depending on the material. So therefore, the resistor is part of the circuit that resists the flow of current. So there are three things here now. There is potential difference, or the energy provided by the battery. There is a flow of current from one terminal of the battery to the other terminal of the battery that passes through the wire. Third, there is a part of the circuit that resists the flow of the current. Then this resistor is measured in resistance. Okay? So measured in a physical quantity called resistance. Okay? Then resistance, its SI unit is ohm, and represented by a Greek uppercase letter, omega. Okay? Voltage, the one that drives the potential difference between the two terminals, okay, is measured in volts. And it's represented by uppercase V. Current, its SI unit is ampere, and abbreviated by uppercase letter A. Okay, so as you can see here, like current, you may say like, didn't you say current is measured in charge over time? Charge over time means coulomb per second. Yes, 1 coulomb per second is equal to 1 ampere. Okay, so 1 coulomb per second equals 1 ampere. All right, so now you know the idea of like what voltage is, what current is, and what resistance is. Then probably, you know, we can look at like the different elements of a circuit then. Okay, so next slide. All right, so then a schematic representation. So every circuit is represented schematically. So even in your house, like for instance, somewhere wherever you have the breaker, you may see some diagrammatical representation of the circuit, you know, what it shows, where the fridge is, where, and so on and so forth. Okay, so diagrammatically it's represented like this. Every time you see a line, it means a wire. Resistors are represented by a zigzag kind of zigzag line. Okay, this is a plug. Whenever you see two parallel lines, one short, one long, that is a battery. And of course there is a switch, and capacitor, you don't have to worry much about it, because we're not going to talk about like a circuit that contains capacitors. At least it's not in the scope of this class. So the main items for our general physics course: wire, resistor, battery or potential difference source, and then sometimes a switch. Okay, those are the items that we will be looking at. Then what is the relationship between current, resistance, and voltage? Then according to Ohm, because there is Ohm's law, the electric current flowing through a given portion of a circuit is equal to the voltage difference across the portion divided by the resistance. So in terms of mathematics, that equation is represented as this: I equals V over R, or voltage is equal to R times I. Okay, all right, so this is what Ohm's law is. This is the thing that we tried to verify during our lab session. Okay, then all right, then now the simplest circuit is a battery or a cell, a wire, and then a little bulb. That's it. But what if you have now multiple batteries? What if you have now multiple resistors, right? So when that happens, then you're going to have a little more complicated kind of circuit. Okay, so there are two different ways that you can connect a circuit. You can connect like resistors. The first one is connecting resistors in series. Okay, in series connection means like resistors are connected like end to end. What do you mean by that? Like you have a bulb, like if you look at this example, you have a bulb. One side of the bulb is connected to another side of the bulb, and the other side of the bulb is connected to, of course, the battery's terminal, and so on and so forth. You see how they are connected? They are connected end to end. So how do you represent them? Schematically, that means diagrammatically. A battery is always represented by two parallel lines, one short, another longer. Always the longer line represents the positive terminal, whereas the shorter side represents a negative terminal of the battery. Okay, so in this particular case, you know, you have a resistance here. You can call this resistance 1. You can call this resistance 2. Okay, from conservation of energy, the total amount of voltage that you have here, let's say the total amount of voltage that you have here in a series circuit is equal to the sum of the amount of energy being dissipated in first resistance plus the amount of energy or voltage dissipated in the second. Okay, that means if you have a series circuit, you can prove this in a better way, but I'm not gonna go through that. So that means the total voltage that is starting from the battery is equal to the voltage in the first resistor plus the voltage in the second resistor. If you have a third resistor as you see it here, what are you going to do? You will add a third resistor, a third voltage. So the total voltage starting from the battery or within the circuit is the same as the sum of all the voltage that you get. Okay. But according to Ohms, we mentioned that like voltage is current times resistance or resistance times current. So if you look at here in a series circuit, the current, when it starts to flow from the positive terminal to the negative terminal, right? Current represented by I. If you look at it, like the current doesn't have any alternative path. It has to pass through R1 and it has to pass through R2. It's like, I don't know, sometimes you might have encountered like faulty Christmas lights. Like if one of the bulbs are dead, like pretty much several of them are not working. Okay. Why do you think that is happening? The reason is like if this guy is dead, it means like there is no passage of current to the next one, because this portion is connected in a series fashion. Okay, so that means you don't want to wire your home network like in a series fashion. Why? Because if the TV is off, then everything will be off. No, that's not the right way of having your network or your circuit at home. Okay, so therefore in a series circuit it's just simply why that happens, because the current has only one path. It passes through one and then it goes and then it passes through the second one. If there's a third one, it passes through the third one, and so on and so forth. If any one of them dies, then that means there's no an alternative path for the current to go through to the second resistor. Okay? Then as a result, because of that, current, the amount of current that starts from the battery, right, is the same current will pass through the resistance one, the same current will pass through resistor 2. So as a result, like current is constant in a series circuit. In series, I is same everywhere. So the amount of current passing through resistance 1 is the same as the amount of current passing through resistance 2, the amount of current passing through resistance 3, and so on and so forth. So if someone asks you like, what is the total amount of resistance in the circuit, then it's easy. Just simply add them all together. Okay, the sum of all of them. So this is a good example here. So if someone asks you like, what is the total amount of resistance in this circuit, then R equivalent is just simply the sum, because this is a series circuit. So it's going to be 15 plus 20 plus 25 equals 60 ohm. That's the equivalent. The equivalent resistance means like, so in a series circuit, the total resistance is just like the summation of the individual ones. So how much total resistance, or how much total resistance is offered by the circuit. But on the other hand, the voltage, the total voltage, that means like that the one that is starting from the battery, in this case like 6, is the same, is equal to the sum of the individuals, like voltage 1, voltage 2 plus voltage 3. Okay. As I already mentioned, since the current doesn't have any alternative path, then the current that is starting here is going to be the same as the current passing through this, the current passing through that, and the current that is passing through this. Okay, so current is the same. Okay, current is the same. So I1 passes, I equivalent, you can call it I equivalent or I total. You can say total because it's, so that total amount that passes is the same everywhere. I total equals I1 equals I2 equals I2. Okay. So an example. So I want you to solve this. Let's say a 9-volt battery is connected to 4 light bulbs, as shown. Then find the equivalent resistance for the circuit. So this is simple, right? So you're given, you can put it like you're given. Say, as always, I like to solve things like using given. Then call this one R1, call this one R2, call this one R3, call this one R4. So the equivalent resistance you can find are equivalent. We already showed in the previous slides. Equivalent resistance, the type of connection that you have here is a series connection. So therefore the equivalent is the sum of the individuals. Okay. So resistance 1 is 4. Resistance 2 is 5. Resistance, oh, I missed it. Resistance 1 was actually 2. It's fine. The order doesn't matter. It's addition. So ohms. So if you add all of those, right, you're going to get 8 ohms, 18 ohms. So the total or equivalent resistance means like if someone asks you like instead of having 4 bulbs, get 1 bulb with the same amount of resistance, then in that case the answer is 18 ohm. Now, second part of the question is what is the total current from the battery? So from Ohm's law, we define that like current is equivalent to volt over resistance. So in this particular case, the total current starting from the battery, so therefore, the total voltage, then the total voltage is 9 volt, that's given. Divide that by resistance. Which resistance? The total resistance, of course. So therefore, this will be 9 divided by 18 ohm. Then that will be 0.5. What is the SI unit of current? 0.5 ampere. Okay. So, simple. As you can see here, like it's in a series circuit, it's pretty much a straightforward kind of approach. Then you can follow and then you can solve the problem. If someone asks you like to draw the circuit, then circuit, how many resistors do you have? 4. 1, 2, 3, 4 of them. Connect them with a straight line. Okay, and then of course that is connected with a battery. Battery is represented by by one short and one long line. Okay, so here's where your voltage is. Here are your R1, R2, R3, and R4. Okay. Then the second type of circuit is resistors in parallel. So what if the other way of connecting resistors? The way you see it here, it's a nice sketch, and you know, credit to person who made it. It's like you have a battery, and then you connect only one side of the wire with the next element, instead of, like, you know, holding things hand in hand. Now it's like instead of, like, it's just, you know, consider like you're standing here and then holding your friend's hand here, kind of thing. That's serious. But in a parallel, it's like one is leading, the other one is following behind, and so on and so forth. So when that happens, look, current is coming from the battery, from the battery, from the battery. When it reaches here, there is a junction point. There's a junction point that, you know, we put it here. And if there is a junction point, what happens? Current can go through this, or current can go through this. If resistance 1 dies, then it's fine. There is another alternative path for the current to pass through. Okay, that's how it's different. So your house is connected in a parallel connection. Your computer, your fridge, your dishwasher, your TV, they must be connected in a parallel circuit. One dies, that's fine. The rest of them still will be working. Okay. Okay. So yeah, you can look at the diagram here too. So, you know, the current starts flowing from the positive terminal. So keep in mind. Of course, you may say like, oh, but Professor, you were saying electrons are the one that flow. Yes, electrons flow in this direction, but the convention says current is flowing from the positive to the negative terminal. So it's coming here, and then when it reaches here, then the current is going to, some of it will come to this side, then some of it will come to this side, and some of it will come to this side. See? So it's going to come here, and when it reaches here, some of it splits to this and that. So there's always an alternative path for the circuit. But the potential difference between the corners, like, you know, the potential difference between the two terminals here is the same as the potential difference between the two terminals and the potential difference between this terminal. So therefore, voltage is constant in all the resistors. That means if 9 volt is starting from here, you get 9 volt, you get 9 volt, you get 9 volt. You see? Now you can also imagine, like, at home in your house. That's why, like, every outlet that you see is rated as 110, 120 volt. Why? Because voltage at every point you're going to get in a parallel circuit is constant. It has its own advantage. That means, like, the amount of voltage is not going to reduce in your house. You're going to get the same amount. Of course, the current is a different story. Whereas the current is going to be the sum of the individuals, because some of it will drop through R1, some of it will drop through R2, some of it will drop through R3. So therefore, the total current in the circuit is the sum of the individual currents. Things will get a little more complicated when it comes down to the resistor. The equivalent resistance is going to be how? It's not going to be the sum. It's not going to be the same. Rather, it's going to be 1 over the total, or the equivalent resistance in the circuit will be 1 over the summation of the individuals. All right, 1 over the summation of the individuals. Okay, So maybe, like, you know, you can go through the calculation. I mean, this slide is I don't want you to look at it. It's I put it just for the sake of completion, but eventually, if what happens is, like, you're gonna get the same. So let's get back to our examples, and then let's go through those examples a little bit quickly. We already solved this, remember. To start resistance in a series, because this is series, you just simply add the individual resistances. Okay. Then the total current is going to be just whatever total voltage that you get, divide that by the total resistance, okay, or the equivalent resistance. I don't like to, in a series you can call it the total resistance because you are going to add them all, but in a parallel connection it's better to call it like R equivalent. Then the voltage, how much voltage is dropping here, how much voltage is dropping here, how much potential difference is dropping here. How do you find it? By just multiplying the current and this. Where did we get that equation? You know, in the second or third slide, when I was talking about like Ohm's law is applicable at each resistor. So therefore I times R1 will get you V1, I times R2 will get you. Okay, now two resistors connected in parallel. If they are in parallel, what did we say about the voltage? The voltage across is going to be the same. So at the tip of your finger you will know how much would be V1. The same as the batteries. You will know how much will be V2, the same as the batteries. So V1 here, V1 there will be the same. Now the challenge is what? What did we say? The equivalent resistance is the sum of the inverse of the individual resistors. Okay, so if someone asks you, we will limit ourselves to 2 resistors. You can go for 3, you can go for 10. It's not going to be a problem once you understand what is happening. So 1 over 10 plus 1 over 10. Keep in mind, this is 1 over equivalent. It's not R equivalent by itself. So therefore, if you do this, what does it mean? Common factor 10. 10 divided by 10, 1 times 1 is 1. Same thing, 10 divided by 10, 1 times 1 is 1. This will be what? 2 over 10, which is 1 over 5. 1 over 5 is 1 over R equivalent. So therefore, to get R equivalent, what will you do? Flip this guy. If you flip the left hand side of the equation, you must do the same thing on the right hand side. That's the law of mathematics. You can't change it. Therefore R equivalent equals 5 over 1 ohm. 5 over 1 means 5. Always students, they do all the calculation and they come here and then they leave it like 1 over 5. But 1 over 5 is not really, especially when you deal with, like, you know, exams, you know, it's mostly like students just leave things like so here's the solution by the textbook, but I like to explain things, so that's why I resolved everything for you. Then the total current, probably total current can be found by what you already found, the resistance, which is 5. Then the total voltage divided by the equivalent resistance, in this case 6 over 5. Okay, 5 is just, it came from this calculation. All right. Then you can apply Ohm's law at the individual resistor locations to find the individual currents. So current 1 will be V over 1 R1, current 2 will be V over R2. Okay. So there is a parallel circuit. I mean, I'm going to let this one let you solve it. It's fine. Okay. Then one last item before we wrap up. So power. So for instance, like power, you are buying a lamp, most likely, you know, it shows like 60 watt, and oh, this is number 60, this is number 100, this is number 40. People say it's that way, but that's the rate of power, the rate of, you know, remember when we defined power in chapter, I think it's in chapter 5, what did we say? It's the rate of consuming, or the rate of work done. So in this particular case, it's going to be the rate of what? The rate of dissipating energy. How fast a certain object dissipates energy. So forget the other part, but just in terms of voltage and current, this is how you find power. The power dissipated or consumed, however you mention it, by a resistor can be calculated as voltage multiplied by current. Okay, voltage multiplied by current. All right, so P is equal to V times I. So then, you know, you may also find P as V multiplied by, we know that current is V over R. So you can also find power as V squared over R. Okay. You remember what was the SI unit of power? The SI unit of power was watt. Okay. So you may also replace V by I, and then you may also calculate. So you have three individual equations to calculate power. Okay. So one is just simply P equals V times I. The other one is P equals I squared times R. The other one is P is equal to V squared over R. All right. So one example, what is the power dissipated in a 20 ohm light bulb powered by two 1.5 voltage battery in series? Okay, so calculate the total voltage first, since they are connected in a series. Then what happens? Then you will have like 1.5 plus 1.5, that's total voltage. Then you already know, like, you can find the current, but it's okay, you can also find it without the current, right? So if resistance is 20, then current is total voltage divided by R, then therefore it's going to be 0.15. Then power is what? Voltage times current, right? Voltage times current. So power equals voltage times current. Then you know voltage, which is 3. The total voltage times the total current is 0.15. Multiply this, much value are you going to get? 0.45. The SI unit of power is watt. Okay. So with this we are wrapping up like just the material. So thanks for your patience.